Imagine a world where reality isn't fixed, where particles can exist in multiple places at once, and where the very act of observing something changes its nature. Welcome to the quantum realm, a realm that defies our everyday intuition and challenges the very foundations of reality. This is the frontier of scientific discovery, where the quantum revolution is unfolding before our eyes, transforming not only our understanding of the universe, but also the technologies that shape our lives. There was a time when scientists believed they had a firm grasp on the universe. Newton's laws reigned supreme, predicting the motion of planets and the trajectories of cannonballs with remarkable accuracy. But beneath the surface, a revolution was brewing. Before to go further, do not forget to subscribe, share, like, and start the conversation in comments. In 1900, a German physicist named Max Planck was grappling with a perplexing problem: the nature of black-body radiation. There was a problem in the classical description. The classical description of black-body radiation gave rise to the ultraviolet catastrophe. To solve this problem, he made a radical assumption. Energy wasn't continuous, but rather emitted and absorbed in discrete packages, like tiny bundles of light. These packets he called quanta. Building upon Planck's idea, Albert Einstein proposed that light itself was quantized, existing as particles he called photons. This revolutionary concept explained the photoelectric effect, a phenomenon that baffled classical physics. Niels Bohr, a brilliant Danish physicist, took these ideas further. He developed a model of the atom where electrons orbit the nucleus in specific quantized energy levels. This model, though imperfect, marked a significant step towards understanding the inner workings of atoms. Before to go further, do not forget to subscribe, share, like, and start the conversation in comments. In the 1920s, a new generation of physicists, including Werner Heisenberg, Erwin Schrödinger, and Wolfgang Pauli, revolutionized our understanding of the atomic world. Heisenberg developed matrix mechanics, a mathematical framework that described the behavior of subatomic particles without relying on classical concepts like position and momentum. Schrödinger, on the other hand, developed wave mechanics, describing particles as waves governed by a famous equation that now bears his name. These seemingly different approaches were later shown to be mathematically equivalent, providing a more complete and powerful description of quantum reality. In the mid-20th century, a group of brilliant physicists, including Albert Einstein, Boris Podolsky, and Nathan Rosen, were grappling with the strange implications of quantum mechanics. They devised a thought experiment, known as the EPR paradox, to highlight what they believed to be a fundamental flaw in the theory. The EPR paradox involved two particles that were entangled, meaning their properties were linked in a way that defied classical understanding. Einstein and his colleagues argued that quantum mechanics must be incomplete, as it seemed to allow for faster-than-light communication, violating the fundamental principles of relativity. However, in the 1960s, physicist John Bell took a different approach. He devised a set of mathematical inequalities, now known as Bell's inequalities, that could be used to experimentally test whether quantum mechanics or the local hidden variable theories proposed by Einstein and his colleagues were correct. Over the years, numerous experiments have been conducted to test Bell's inequalities. The results have consistently shown that quantum mechanics violates these inequalities, confirming that entanglement is a real phenomenon and that our classical understanding of reality needs to be revised. The development of quantum mechanics has had a profound impact on our world. It's the foundation of modern physics, underpinning our understanding of everything from the smallest particles to the largest structures in the universe. From lasers and transistors to nuclear energy and quantum computing, the applications of quantum mechanics are transforming our lives. Our world is intrinsically quantum and non-local. So why we do not have experience of quantum phenomena on a macroscopic scale? Quantum decoherence is a process that destroys the delicate quantum states of a system, causing it to lose its quantum properties and behave classically. Quantum decoherence occurs when a quantum system interacts with its environment. The environment can be anything from stray particles to electromagnetic fields. This interaction causes the system to lose its coherence or the ability to exist in a superposition of states. As a result of decoherence, the system becomes entangled with its environment and its quantum properties are lost. This is why we do not experience quantum effects macroscopically. Quantum mechanics. The very name evokes images of the bizarre and the inexplicable, but what exactly is it? At its core, quantum mechanics describes the behavior of matter and energy at this fundamental level. Unlike classical physics, which deals with the everyday world of objects, quantum mechanics operates in a realm of probabilities and uncertainties. It tells us that particles can exist in multiple states simultaneously, a phenomenon known as superposition. It tells us that particles can be entangled, connected across vast distances in ways that defy our classical understanding. And it tells us that the very act of observing a quantum system can fundamentally change it. This leads to many different interpretations of quantum mechanics, each offering a unique perspective on its mysteries. Before to go further, do not forget to subscribe, share, like, and start the conversation in comments. The Copenhagen interpretation, perhaps the most well-known, suggests that the act of measurement forces a quantum system to choose a definite state. The many worlds interpretation proposes that every possible outcome of a measurement actually occurs, leading to a branching of realities. And the pilot wave theory suggests that particles are guided by an unseen pilot wave that determines their behavior. The journey of quantum mechanics is far from over. Scientists continue to explore its mysteries, pushing the boundaries of our knowledge and unlocking new frontiers in technology. The quantum revolution is still unfolding, and its impact on the future of humanity is yet to be fully realized. Do not forget to subscribe, share, like, and start the conversation in comments.